In the name of God, Fluid Mechanics from Frank M. White, 7th edition, Chapter 1. The new update of Microsoft Whiteboard is an ability to study in a blackboard type. So our two previous courses, static and dynamics, were studied in whiteboard, and fluid mechanics will be studied in blackboard type. So anyway, dimension and units is the next section. We are going to talk about dimension and units. In the previous courses, static and dynamics, we are widely talk about the dimension and units in two different unit systems, such as SI and British or US customary, which is shown in this table. There is the primary dimension of mass, length, time, and temperature, which in SI units are kilograms, meters, second, and Kelvin. And in the British, we have slots for mass, foot for length, and second for time, and ranking for temperature. And the conversion factor also listed in this table. We can write 1 slot equals to 1 foot equals to 1 second equals to 1 second, and 1 Kelvin equals to 1.8 degree of ranking. Each parameter in engineering have a dimension, and it is useful to checking the answer of problem. For example, checking the accuracy of the given data or desired result data. The primary, for example, for the force, we have NA from the second law of Newton. So we have 1 Newton equals to 1 kilogram multiplied to 1 meter on second square. So with this dimension, we have 4 kilograms, we have N for mass, L on T2. This is the dimension of Newton. 1 Newton equals to NL T2. When you, for example, calculated a force, you can check your answer with dimensional analysis. The British or US customary system and SI also described in the previous chapter, such as previous courses such as statistics and dynamics. You can use them, but in this level of engineering, you should familiar with this system of units. So we are going to continue our description of the introduction chapter with the next section, properties of the viscosity velocity field. Properties of velocity field. In a given flow situation, the determination by experiment or theory of the properties of fluid as a function of position and time is considered to be the solution to the problem. In almost all cases, the emphasis is on the space-time distribution of the fluid properties. One rarely keeps track of the actual fate of the specific fluid particles. This treatment of properties as continuum field functions distinguishes fluid mechanics from solid mechanics, where we are more likely to be interested in the trajectories of individual particles of the system. So we have two description of velocity field, Eulerian and Lagrangian description. There are two different points of view in analyzing this problem in the mechanics. The first view, appropriate of fluid mechanics, is concerned with the field of flow and is called the Eulerian method of description. Eulerian method of description. Connected with the field of flow and is connected with the field of fluid. Flow. In the Eulerian method, we compute the pressure, for example, of the flow pattern, not pressure change in time. So in this case, we have, for example, P equals to a function of spatial and temporal change. But in the Lagrangian, it is Eulerian statement. And if we interpret P as a time in the flow, especially in the fluid line, we have Lagrangian statement. In Lagrangian definition, which follows an individual particle moving through the flow. Individual particles moving through the flow. The Lagrangian approach, which is more appropriate to solid mechanics. So we have taken the more appropriate for solid mechanics. Will not be treated in the fluid mechanics in this course. However, certain numerical analysis of sharply bounded flows, such as the motion of isolated flow droplet, are already conventionally computed in Lagrangian coordinates. Flow dynamic measurements are also stood to the Eulerian system. For example, when a pressure probe is introduced into a laboratory flow, it is fixed at a specific position, for example, X and Y and Z. Its output does contribute to description of the Eulerian pressure field, which shows the in a, for example, look at this boundary volume. We have a some fluid if we choose a, for example, a point here, X and Y and Z, the interpretation of this point in time should be right X, Y, Z, and T. This is the Eulerian method. And if we consider the point, for example, that we want to have the information of this point of flow, that in T1, T2, it is a T3, T4, T5, and T6. So in this case, we can express the pressure of point A, which moves with the fluid, as PT, without considering the location of point A in our control volume. So T1 to Tn, it is the Lagrangian method of description in the fluid mechanics. In the fluid mechanics, in this course, we are dealing with only the Eulerian description in fluid mechanics. Velocity field in the Eulerian method. Foremost among the properties of a flow is the velocity field. Foremost among the properties of a flow is the velocity field, as we stated here. In fact, determining the velocity is often tantamount to solving a flow problem, since other properties flow directly from the velocity field. Next chapter is devoted to the calculation of pressure field once the velocity field is known. This course not dealing with the heat transfer problems, but there is some references to the temperature field from known velocity field relation description, and we are going to calculate the other properties of a flow field. In the vector form. At first we have a velocity field of T equals to 3 component of velocity we have and the use of U, V, and W for the velocity components instead of Vx, Vy, and Vz, for example,
is the result of an almost unbreakable custom in fluid mechanics. Much of this course, especially in next chapter, is connected with finding the distribution of the velocity vector v for a variety of practical flows. The acceleration field vector, which stated as a equals to dv on dt equals to plus this is the acceleration vector occurs in the Newton's law for a fluid and is very important. In order to follow a particle in Eulerian frame of reference, the final result for acceleration is nonlinear and quite complicated. Here we only give the formula for the acceleration field vector, where u, v, and w are the velocity components. From the previous equation for v, we have the v vector as these three components. We shall study this formula in detail in next chapter. This is the material deviation of the velocity on the that give us a acceleration field. The first is the spatial, this is the temporal part, and the second is the temporal and spatial acceleration due to temporal change and acceleration due to spatial change. Anyway, more description about the acceleration field is in the chapter 4 in this study. Thermodynamics properties of a fluid. While the velocity field v is the most important fluid property, it interacts closely with the thermodynamics properties of the fluid. We have already introduced into the discussion the three most common such properties. Pressure, three most common one, pressure, two, density, and three, temperature. These three are constant companions of the velocity vector in flow analysis. Four other intensive thermodynamics properties become important when work, heat, and energy balance are treated. So we have also intensive properties, work, heat, and energy. According to these three fluid properties, we may have, for example, internal energy, enthalpy, entropy, specific heats, Cp and Cv. In addition, if the friction and heat conduction effects are governed by the two so-called transport properties, so if we have also friction and heat conduction, we will have these properties of fluid, also coefficient of viscosity, and thermal conductivity. So we are going to have some short definition for fluid properties. Pressure in fluid mechanics is the stress at a point in a static fluid is fluid, and it is in the dimension of pressure, and units of pressure and dimensions are, for example, 1 atm. The units of pressure equals to 2116 pound force on foot square, and also equals to about 10.5 Pascal, and the dimension is P F on A, Newton on L2. Newton is M, L on T, 2 on L2. M on TL2. The dimension of pressure. The next property is temperature. Temperature T is related to the internal energy level of a fluid. T is related to the internal energy level of a fluid. It may be very considerable during the high speed flow of a gas, although engineers often use Celsius or Fahrenheit scales for convenience. Many applications in this study requires absolute Kelvin or vacuum temperatures. So the units are Celsius or Fahrenheit, Kelvin, or Rankine. This study we may use temperature as Kelvin and Rankine for SI, and for US or British. And the relation between Kelvin, 1 Kelvin equals to centigrade plus 273.60, and 1 Fahrenheit equals to Rankine equals to Fahrenheit plus 16. You can use some software or application to change Kelvin to Rankine, or for example Celsius to Kelvin to Fahrenheit. Anyway, the next is density. These properties of fluid density. The density of a fluid denotes by rho. Is the mass per unit volume, as we know from our knowledge, rho m on v. Density is highly variable in gases and increases nearly proportionally to the pressure level. Density in liquids is nearly constant. The density of water and other fluids are available in the table. The next definition in a specific weight. The specific weight of a fluid denoted by a specific fluid. Note by gamma n equals to the volume on equals to its weight per unit volume. Just a mass has a weight mg, density and excessive weight are simply related to this relation. The units of gamma are weight per unit volume. In standard Earth gravitational, G equals to, and in SI, and in British or US, G equals to 32.174 foot on square. So if we have the density of a fluid, we can calculate the specific weight. Specific gravity. Specific gravity is the next. Denoted by Sg, equals to, for gases, rho gas or rho air for fluid, raw fluid, on raw water at 4 degrees of Celsius is the ratio of fluid density to a standard reference fluid, which in gases the standard is air and in the fluid the standard is water. And the next is potential and kinetic energies. The potential energy widely discussed in the statistical dynamics also. The potential energy equals to the work required to move the system of mass m from the origin to a position vector r. For example, we have a two position from 1 to 2r. The potential energy is the required work to move the system of mass m from the origin to a position vector r. R equals to, for example, the potential energy and against the gravity field G. Its value is minus mg multiplied to the position vector. Potential energy U usually. The kinetic energy equals to the work required to change the speed of the mass from 0 to velocity v. The kinetic energy equals to the work required to change the speed of the mass from 0 to the work required to increase the speed or change the speed from of a mass m to a from 0 to velocity of v, which shows visually equals to this relation. And by common convention, the total stored energy E per unit mass in fluid mechanics is sum of the three terms, which are the, so we can write the stored energy E, total energy equals to U, internal energy plus kinetic energy and plus minus G dot R. It is a stored energy per unit mass. state relation for gases. The next is definition for state relation for gases. Thermodynamic properties are found both theoretically and experimentally to be related to each other by state relations that differ for each substance. As mentioned, we shall confine ourselves here to single-phase pure substance such as water in its liquid phase. The second most common fluid, air, is a mixture of gases, but since the mixture ratio remains nearly constant between the specific temperature, in this specific temperature, air can be considered to be a pure substance. All gases at high temperature and low pressure relative to their critical point are in good agreement with the perfect gas law, which we indicated as below. Perfect gas P equals to and R equals to gas is constant. Gas constant where the specific heats Cp and Cv will be described later and are available in the tables. Each gas has its own constant, and it is equals to each gas R on the molecular weight of gas, and R is a standard constant, which in its R unit we have joule on K mole Kelvin, and in the British we have this relation for this quantity for standard constant of gases. Point on slug mole ranking. Anyway, so we can calculate the constant of each gases in relation to the molecular weight and the standard constant of gases. The standard specific Cp specific heat for Cp and Cv equals to and equals to the relation between the internal energy and the specific heat du plus equals to a function of T, where du is Cv T dt. So we can have an integration to calculate Cv or u, and Cp equals to P and where the H minus Cp a function of t dt. If we have a relation of Cp, we can calculate dh for example as a function of t. The ratio of a specific heat of a specific perfect gas is an important dimensionless properties in compressible flow analysis, which is equals to K equals to Cp on Cv is dimensionless and equals to a function of t where it is usually greater than 1. As a first approximation of calculating the Cp and Cv for air, we have K equals to 1.4. So Cp equals to Kr on K minus 1 equals to minus I, and Cv equals to there is also some statistical relation of states for liquids that are not applicable in this course. The next properties of fluid are available in next video, which are discussed.